some stuff, so at least we can have it up and read together. So this first example is one where we're looking at simply a body that's undergoing two different forces on it, acting with a certain lever or distance from the pivot. The pivot is considered O, the origin, and the question really is, what's the overall torque acting on this object? That's really what it's asking. And the way to think about this is just simply like think about, all right, if you had like a seesaw and you and your brother sat on each end, if one of you is heavier than the other, it's going to rotate in that direction. Well, if you suddenly move further from the fulcrum, it changes that up, right? Because it increases or decreases your lever arm, and that's all that's happening here. Something that you guys already probably talked about was that you use RF sine theta. Is that okay? So you know that already. That's good. Where theta has to be the angle between the lever arm and the force. Keep that in mind. Theta is always the angle between the lever arm and the force. For example, if you were given an angle that was with respect to the normal, right? This is called the normal here. If you were given this angle alpha, see what I just drew in the top right? That's not the angle you use. You use 90 minus that angle. Okay, so it's always the angle between the actual force and the lever arm. What is the lever arm? That's this right here. The direction along which the direction between the pivot and where the force acts. If you follow this and extend this line indefinitely, you'll see that this is the lever arm, or this is the direction the lever arm acts, and this is the actual force. So this is the angle we're going to use always.
Theta subscript 2.
Theta subscript 2, that's what that says, yes. And on this side, theta subscript 1, just simply because they're two different angles that are given in the problem. So what you need to think about is which way is it going to turn? That's really the question you have to ask yourself. So if you were only applying force 2, which way would it turn? Yeah, it would turn this way. Again, think about, here's your piece of paper, you push down on this side, it's going to rotate that way with F2. And the other side, which way is it going to rotate? Counterclockwise. It's not about memorization, so don't memorize if the force is down on the right, it goes clockwise on the left. I mean, it works out that way, but just think about it conceptually. You're pushing down on an object on the right, it's going to go clockwise. Pushing down on the left, it's going to go counter or anti-clockwise. Do you use anti-clockwise or counterclockwise?
Counterclockwise.
Does your book use that also? Okay.
I didn't even know anti-clockwise.
It's the same thing. I've heard both interchangeably. You know, think about it, counter, anti. So in this problem, all we have to do is take a look at the sum of the torques. If we're trying to find the net torque acting on an object, we talked last class, and I reiterated that tau net equals I alpha. But does this problem ask about moment of inertia? No. Does it ask about acceleration? No, nothing about that. So there's no need to set it equal to I alpha. You're simply finding the net torque. And that's equal to torque 1 plus torque 2. Okay, I'm going to use negative and positive signs, obviously, when necessary. So if I look at force 1, which way have you guys in this class been considering positive?
Counterclockwise.
The book used counterclockwise. So if we're considering counterclockwise positive, right, this way, that means that F1 produces a positive torque. Again, if we consider this to be positive, F1 is positive. So this should be positive, and then what would tau 2 then be? Yeah, so we're going to change that in the middle there, and make this a negative. But again, I'm able to see that based on my understanding of directionals. It doesn't matter, though. Remember, it doesn't matter. And as Mr. Donachek talked about the idea that some books consider down positive with acceleration, I think you're texting that also.
Gene Coley.
Yeah, they'll call 9.81 positive even during projectile motion when it's acting down, and they'll consider this the positive y direction and this the negative y. It doesn't matter. We just happen to adopt the concept that down was negative and up was positive with our normal Cartesian coordinate, but it doesn't really matter there. So tau 1 is going to be RF sine theta. Now R is R1, F is F1, and sine theta 1. And then simply the second one, R2, F2, sine theta 2. And that's really it. You're just going to plug in at this point. Okay, plug in R1, R2, F1, F2, and then your angles. Everything's in SI units, no need to change anything at all. What will we get as an answer? What did you guys get? Anyone got an answer for this one? Brianna, what do you got for this one? Yes, guys, listen. Arthur, relax. I know you're talking about. You're talking over your classmates. Sorry. Negative 3.85 Newton meters. Recognize that this is not a joule, even though a joule is a Newton meter. You know that, by the way? Think about it. Work is defined as force times distance. Force is newtons, distance is meters. So it's weird to recognize that torque and energy are actually the same units, even though energy is not considered Newton meters, it's considered joules, right? But torque is left as Newton meters. Kind of a weird thing. Think about that. Maybe do a little research as to why that is. It's kind of interesting. So let's take a look at this next example. The next one is 47. So let's put this one here. Give me 1 second. I think this is 47 here, right? Yes. You'd like to do it on the board, is that what you said? You can if you want. Did you get this one right? Do you have an idea? Did you check in the back? Odds are in the back, boys.
I think so, it's right.
What do you get?
It's right. 4.6 Newton meters.
Yeah. Now let's do it.
Okay.
You want to actually just write it instead? Here.
Sure.
No, stay.
Oh.
Stay. Good.
Oh, Apple Pencil?
Oh, yeah. Actually, it's on Grippy Tool, so grab that one right there. So Arthur's going to talk about what he's doing and write what he had here.
So, tau. Oh, geez. I'm going to be honest, guys. I have terrible handwriting, so just be
Try to do
prepared.
your best.
So, tau equals RF sine theta. And I know F equals mg, right? So when the resulting pendulum is 30 from the vertical, so then I plug stuff in, and theta in this, is it 180 minus 30, right?
It's good. Well, it's going to be 90 minus 30 in this case.
90 minus 30, yeah. Okay, so, and then I guess I can just plug stuff in, right? 1.25 times 0.75, right? Times 9.8 times sine of 90 minus 30, so 60, right? Equals 4.6 Newton meters.
I did have 30 still, but let me just see what I wrote. Draw yourself a diagram.
Maybe it's 30. I think
It actually is 30.
I think
it's
it is
not,
30,
it's not
yeah.
60, it's 30. I'll draw
Wait.
a diagram in a second to show you the geometry. It's hard to explain just saying it. Give me a second. I'll draw it
Alright,
out.
sorry.
The eraser is right here.
This one?
Yeah, it's not the same kind of eraser as notability does. Just be careful. It's going to erase a lot. Or erase nothing.
Or
Just
erase?
Just cross over. It's fine.
Okay.
Yeah, it's a glitchy app sometimes. I know that.
Okay.
So, draw the diagram. Go ahead. So,
Okay.
at the end of the diagram, we have a little mass hanging on the end, right? Draw yourself a vertical. All right. Our angle's 30 right there. Now, here's the issue with this kind of a problem. For torque, we have to consider the force that is perpendicular to the lever arm, right? The force perpendicular. So, from the mass, draw a straight arrow down as mg. So we know that it's the mass and the weight of the object acting down. Now, that's not perpendicular, unfortunately. That's not perpendicular, it's the lever arm. Use the pointing tool right here. And let's just point to the lever arm so we see the whole lever arm. So the lever arm and mg are not perpendicular. Does everybody see that? So normally you would just use RF sine theta and it works
It's
automatically.
150.
It happens to work out this way,
150.
the RF sine theta, because sine 30 and sine 150 are the same value.
Okay.
That's
Yeah.
why that works out. But specifically, I want you to see this. Draw yourself a vector perpendicular here. Like that.
Geez, sorry.
So draw yourself a vector like
Yeah.
that. Yeah, you gotta use the drawing tool, unfortunately. No.
Oh,
Undo
sorry.
that.
Undo that. Jeez.
Perpendicular to the lever arm itself.
Oh, to the lever arm itself. Okay. Well,
The undo feature.
which one is it? Sorry. Got it.
Draw
So
yourself
it's
a-
gonna be like something like that,
Yes.
right?
That's the force we're looking for. The force that's acting this way, because it's perpendicular to the lever arm. So I need to create this triangle here. This is kind of a weird triangle to create, so create a triangle here. Yeah, there's your right triangle. So your goal is to actually find the length of this part of the triangle right here, use. And if you look at this angle of 30 degrees here, okay, if I continue this with a dashed line, continue the lever arm with a dashed line, that angle right there is 30 degrees also.
Oh, because
Because these lines
Parallel
are vertical,
lines.
and they're cut by a transversal.
yeah.
So that angle is 30 right there, which makes this angle right in here 60.
60. I can't really write it. You
I
want
know,
to
it's tough to write. Zoom in here, actually. Here, grab this, press this one right here.
press that. There we. Oh,
Yeah.
ooh, that's a. Is that okay?
That's perfect, yeah.
Okay.
So draw out a 30 right here.
Mm.
Go back to your pen tool.
30.
Yep.
60.
Good. And then the other 30 is down at the bottom there. Okay, so it's really
30.
36 to 90, obviously. You notice that. But the concept is that we need to find this length. Point to this one. We need to find this length right here. That's what we're trying to figure out.
Which
We'll
one's
know that?
that?
It's a little way ahead.
That one. We're trying to find
That's the
that
length
one.
we're trying to figure out right there. Okay, because that's the lever arm, or that's the force that's perpendicular to the lever arm. So if you just look at this diagram, you have the actual hypotenuse is mg, and you want not the, well, depending on which angle we're looking at. If we're using this 30, this angle down here, right, and we have the hypotenuse, we want the opposite in this case, the opposite from this. And opposite of our hypotenuse gives you
Sine.
sine. That's the easy way to come up with this derivation. It's not obvious. Again, I want you to see that it happened to work out that the formula RF sine theta did work, but the geometry in the problem actually affected this answer. Okay, this 30 degrees, if you had used this as 60, what function would you have used?
Cosine.
Cosine, because cosine of 60 equals
Sine of 30.
sine of 30. They're both 1/2, okay? But the concept here is that this little diagram is what allowed you to figure out what the force vector is. It turned out to be RF sine theta, which is really nice. But it won't always work out that way with these different kinds of examples. So you need to always remember that when you have a lever arm, the force you're going to use is perpendicular. So consider where that angle is given. You might have to change up your actual answer for it. Okay?
Okay, and okay,
Yeah, go.
got it. And it. Okay, yeah, I got it.
You sure?
Yeah.
All right, let's take the next one here. Next one is what? 51. Let's see, 51. This is, I think, a pulley system, right? Yeah. And this had two parts to it, so let's go ahead and look at these both. So this figure on the right here, this pulley system, is what we're looking at. The first thing I would think about is free body diagram, right? You're going to need something on these masses so you understand what's happening. So you could start by drawing that if you like. This is the end of the question. Let's pull that. All right, so there's the full question there. So again, we're looking at number 51 here. We're looking at number 51. In the figure to the right, block 1 has a mass given, block 2 a mass given. There's a pulley. The pulley is mounted on a horizontal axle with negligible friction. First of all, horizontal axle here in this case just means into the page, actually, right? Into and out of the page. Although it says horizontal axle, that's kind of, I think personally, an arbitrary statement because this is horizontal and so is this, right? Technically, this is the only vertical. There's two horizontals, X and Z. It's really in the Z direction, the axle. So it's going to rotate about that center there. The radius is 5 centimeters is given. When released from rest, block 2 falls a certain distance in a certain time without the cord slipping. Okay, without the cord slipping. When that happens, what can you easily calculate? What's the first thing you can calculate when you know something moves a given distance, it was initially at rest, in a given time period? What can you calculate that you might need in this case? That you might need?
I was going to say either velocity or acceleration.
Yeah, you'd probably need one of those two things, right? One of those two things are what you're going to need. Now, we don't know VF and we don't know acceleration, so that's what you're really talking about. The velocity at the end of the problem, the velocity when this object is already moving. If we look at the part A and see what is the magnitude of the acceleration of the block, so clearly we're solving for the acceleration first. Do I need information about the other block? Do I need to know how far it's traveled and how long? Why not? No, that's not the reason why. We are doing that, but that's not the reason why. Why do we need the information about the other block? Yeah, of course. Think about it. It's a system, right? You've looked at systems with pulleys. If one object moves down with a given speed or acceleration, the other has to move up with the equal opposite. Okay, that's how they're able to balance one another. So by inherently finding the acceleration of one of the blocks, you're finding the acceleration of the blocks in general. That's part A. Part B asks about the tension in both of the cords. Do you think the tension is going to be the same or different? Just by inspection, not even with numbers. Do you think same or different?
Different.
Why different?
Different masses.
Different masses. What else? One is moving. Yeah, one's moving up, one's moving pulling down, which could also be affected because of gravity, right? So think about the tension itself. Next, what is the magnitude of the pulley's angular acceleration? That symbol, what's the symbol for angular acceleration? The fish, alpha. Alpha, okay? And then finally, what is its rotational inertia? That's I. So we're going to be looking for alpha and I. So think about it. Tau equals I alpha. So if we can get alpha, we can get I. We're going to need tau also, so we're going to need the torque net. To get tau, we need the tension. So this problem is literally stepping you through every step along the way. This is the kind of problem you could expect on like an AP exam where you have like parts A, B, C, and D, where they carry them together. Probably with actually a little bit, no, this is rather difficult because you have kinematics, you have rotational inertia, you have torque, tension, so forces, yeah, so forces and force diagrams. There's a lot going on here. So let's first start with the acceleration. This is the easy part. Who wants to help me with the easy part first? How do I find the acceleration given a time, given a distance traveled, given initial velocity? All those things are given. What equation should I use from kinematics?
Use like the second equation.
Read it to me.
Y equals 1/2 AT. Well, I mean, you have the V in there, but it's V initial 0.
Good. So you have y equals v0t plus 1/2 at squared. v0t drops off because there is no initial velocity. Again, it's released from rest. That's the key word. It's released from rest. There's no initial velocity. So that's our statement we could start with. Solving this for A is going to equal 2y over t squared. Okay, you should be able to solve that back of your hand at this point in your life. 2y over t squared will give us, and remember that y has to be converted. That's given in centimeters. Okay, so 0.75 meters we have to have there, right? So what do we end up getting as a number? What did you get?
1.5,
So I got, is that what you end up getting? 6 times 10 to the negative 2?
Yeah.
Yeah.
Why don't you plug in y as a negative since it's
Why did we plug in y as negative since it's moving down? It says the magnitude. That's what. Yeah. Then you would write negative. Now, guys, it's a great question. Why isn't y considered negative because it's moving down? And usually with your kinematics, you make a negative, right? It says the magnitude, which simply means the overall value, not the actual direction included. But it also actually is important because recognize this acceleration for one mass is positive, and for the other it's so it doesn't make sense to call this negative or positive, even though we're referring to block 2, right? Our data refers to block 2. So yes, block 2 is falling, so it definitely is falling down. But we're finding the acceleration of the whole system. So the whole system's acceleration is 6 times 10 to the negative 2, either up or down, depending upon which mass. Okay? So we're going to use the same number for both masses. In one of those cases, we will show that it's negative, and one will show that it's positive, but that will come later in this. Okay? What are the tensions, T2 and T1 in this case? So we're looking for the tension in the rope. We're looking for the tension here and here. How do we find tension on an object? How do we find tension? How do we find a missing force? What do we always start with? Yeah, sum of the forces. It's useful, though, to probably have a free body diagram of these. If you don't really find it necessary, that's okay. I mean, I don't think you really need to have it, but I mean, it depends on what you like to do. I teach my students to always draw an FBD because sometimes it's hard for them to visualize. But if you guys can visualize already what's happening, then you really don't have to. So if we're looking and thinking about mass, let me pull the diagram out. Mass number 1 or mass number, it doesn't matter which one first. But say we're looking at mass number 1. Okay, the mass on the left. Here's the mass on the left itself. We know that for the mass on the left, we've got, let's see, the weight of the object pulling it down. We've got tension pulling back up. Okay, and then we've got for the second, this is mass 1. For the second mass, give me a sec, I'll show you 1 second. For the second mass, we've got the same thing here. This is pulling up. Still nothing? Now, the diagrams look identical. They look really the same, right? Ft is pulling up, weight is pulling down. That's all I see. What's the difference in the two masses? What have we not written down or shown here in the diagram?
The difference in the two masses.
No, not the masses themselves. I mean, what's the difference in their motion? Yeah, one's going up, one's going down. That's the key. So when I draw my free body diagrams, I traditionally, and it depends on how you like to instruct, but I like to draw it with a dashed arrow to show the acceleration or the direction of acceleration. So the second mass was moving down, so I can write this, and the first mass was moving up, so I can write that. I just draw that there to show what's happening in the actual figure. Okay, so our goal is to find Ft1 and Ft2. We know that Newton's second law tells us F equals ma. We can easily write that. If I were to write this for the first one, I've got Ft1 minus Fg equals ma, where a is positive. In the second diagram, Ft2 minus Fg equals m2a, where a is negative. Where a is negative. So that's, Francesca, that's where I took into account the direction. All right, so this a is negative here, this a is positive over
Can I
here.
write negative MA?
You can, and I think in your text, the text I was looking at an example from does put negative m and m2a, and then they just apply that same number. I write it this way, it really doesn't matter which way you do it, as long as a, the right hand side, turns out to be positive for m2. Yeah, whichever way you'd like to write it is fine. All right, so if we go ahead and solve these, because we know all this information, right? Ft1 is going to equal m1 times a plus m1 times g. Again, where a in this case is positive. Ft2 is going to equal m2a plus m2g, where in this case, though, a is negative. So, Arthur, if you want to put a negative here, like you were saying, that's fine. That's where it would go. Okay? Because, again, this negative would come into play here. So just remember that this acceleration needs to be the negative quantity because it's moving down. This acceleration is a positive because it's up. So that's the big difference, besides the masses themselves, right? The masses themselves also clearly affect the answer here. M2 is different from M1. I assume they're different, right?
Yeah.
We were given two values?
460, 150.
Yeah. So if we plug in numbers here, again, I'm not going to go through the process of plugging in all the numbers. I'm just going to show you what we get. Ft1 will turn out to be 4.54 newtons, and Ft2 will turn out to be 4.87 newtons. The reason it's such a small value, the acceleration itself was very little, 6 times 10 to the negative 2. This is barely moving compared to the acceleration of gravity, 9.81. You see the difference there? Okay, in both cases, mg is going to be far more significant than na. The negative ma, the positive ma, those are very, very, very small values that almost don't even affect the answer. Look at these two, they're very close, aren't they? And you probably thought, why are they so close? When we're adding something to one, yet we're subtracting something from another, it's because mg is really where the actual answer comes from. G is 9.81, the acceleration was 6 times 10 to the negative 2. This is pretty much insignificant when compared to this. Okay? Just to get an idea of why the answers are kind of close to each other. All right, that's B and C. Part D asks us, let's see, I ran out of room, so I can't even go back up. Part D, what is the magnitude of the pulley's angular acceleration? Angular acceleration, what do we use for that? There's one simple formula. I mentioned it at the very end of class yesterday. A equals alpha R. R is given in this case. R is given as, 5 centimeters. So 5 times 10 to the negative 2. A, we determined, 6 times 10 to the negative 2. So if we want to find out what alpha is by itself, we simply divide both sides by R. Alpha equals A over R. Now, the only thing you should recognize, or that's kind of weird, is this. This is meters per second squared. This is meters. The answer is 1.2, and it's something per second squared. What's the unit? Radians. Okay, you do know this. I wasn't sure if you went over all this already. That's good. Good to see. Your meters cancel, don't they? But you can't neglect the fact that it's radians. Why is it radians? I don't see radians here anywhere.
The radios aren't like a real measure of information like that. They just kind of
It is a real measure.
Aren't they like just tagged onto angles? Because he needs like something to measure.
How do you convert between radians and degrees? Yeah, where did that come from? Unit circle. So radians are another measurement of what? Not a measurement of distance, it's a measurement of what? Angles. I heard angles somewhere. Angles. A radian, so 2 radians is actually a measurement of degrees. That's why you can convert between the two, right? So if you think about angular acceleration, in your mind, yeah, the meters cancel, so you can think about degrees per second or like RPMs, other types of units to measure angular velocity or acceleration. Well, when these meters, these two things tend to cancel, the base unit is actually radians there. Okay, which is, it's one of those things that it just like appears, like David was saying. It's not, or you don't know it right away. But know that it's angular acceleration. It's got to have some sort of an angle. An angle is measured in radians. Okay? The last part, part E. Part E talks about finding the overall moment of inertia, I think, right? Or rotational inertia on this object. Well, think about it. Rotational inertia comes from this equation. If we have everything else, well, we've got alpha. It's right there. It's above us. Part D, or part whatever the last part was alpha. The question is, what's tau in this case? How do I figure out tau net? How do I figure out tau net?
So that'd just be force times.
What force, though?
You could use either or.
What do you mean, either or?
Like,
It's definitely not either or.
You have to use one specifically.
Sure, go back to your diagram if you need to. Look at your diagram, look at the pulley system. You've got what force is acting on the pulley? What force is acting on the pulley? Yes, the tensions. You need to use both tensions. Think about the pulley and think about the wire or the cord. It's pulling down, right, on the pulley. Because what's happening? The mass is pulling down, which is transferring that force to the actual rope, which is transferring that applied force to the pulley itself. So as a result, you've got 2 tensions actually pulling down on the pulley, even though they pull up on the mass, right? Mm-hmm. You know how, like, if you think about a rope, if there's a pull this way, there's got to be a pull that way for the rope to be in equilibrium, most of the rope would snap. So since the masses are being pulled up by the tension, the pulley is being pulled down by the tension in each part. So we're not using the weight of each mass. So we have to make sure we're not using mg here. We're using our answers for tension 1 and tension 2, both. And think about the way they would cause this object to turn as a result. Okay? So in this case, we're going to have, let's see, we've got, what are our 2 answers we had from earlier? I wrote them down earlier. And then 4.87. So 4.87 is tension 2 times the actual distance from the center, 0.005? No, 05. 0.05 meters minus 4.54, which was tension 1, times 0.05. I shouldn't even put units if I'm not going to put them in one spot. I can't put them anywhere else. You could factor out, obviously, right? You could factor out that lever arm since 0.05 is the same for both. And that equals I times 1.2. Now, before we go any further, this might be misleading to you, right? Why did I choose one as positive and one as negative? Why is this one positive and this one negative? Forget direction of motion. For a second, just forget direction of motion. Think about this answer here. That's a 1.2, yeah. Think about that answer there. What does I have to be? I's got to be positive. So in the case the test comes about and you forget which way to put each torque, and you know that your acceleration turned out to be positive, this difference needs to be positive, or this sum needs to be positive, right? Because if you got an answer here that was negative, and this was positive, you get a negative I value, and I is always positive. So if you forgot what to do here, that's fine. Now, at the same time, you could also consider the fact that this system was rotating which way? Yeah, because mass 2 was pulling down, wasn't it? And we got clockwise, yet our answer for acceleration was positive. And earlier you told me clockwise was negative, didn't you? So that's what I'm trying to get at. And it doesn't matter which way you call positive or negative, as long as you're consistent in that problem. So because this problem, acceleration was positive, angular acceleration, and we considered in this problem then clockwise to be positive. So as a result, the tension pulling down on the right, which was T2, is going to be considered positive. Again, here's the pulley. Here's T2. Here's T1 pulling down on the pulley. Normally, in your previous class, you would have most likely called T1 positive torque, right? The tension pulling down, the torque as a result, you would consider T1 to be positive because you consider counterclockwise positive. Now, because of the fact that we considered angular acceleration positive as clockwise, T2 would give you a positive torque. That's why 4.87, which was from T2, is positive. T1 is considered a negative torque now in this problem, so we put a negative sign there. All of that comes from the fact that we considered the acceleration to be positive when it was clockwise earlier.
If we had done the whole problem.
If you had just applied a negative sign in the previous step right here, right? Because you're like, you know what? Oh wait, it's going to rotate this way. We've considering that to be negative, so you just tack on a negative here. That's absolutely fine. You can do that. But then these would have had switch. Okay? But the idea I want you to get at is that you're taking a test at the end of this year. You want to do well on that test. Make sure your numbers work. So whether it's complete understanding or using inspection and using your intuition to see, well, this has to be positive, or if this is positive, this has to be positive. So if you had it wrong, what should you probably just do? Switch it. See what I'm saying? Okay, so a lot of the time you should understand what's physically happening, but when it comes to a time test and your answer comes out to be something that doesn't make sense, and you could easily figure out what it was. Oh wait, we did the rotation that way, now it's this way. Switch those two numbers. Okay, because when I did this problem first, I got a negative I value. I'll be honest. Okay, I was doing this problem and I ran through it, and I had this to be positive. Because I didn't apply a negative sign up here because I had all positive numbers. Look, the acceleration is positive, the radius is positive, I wrote down a positive number. And then because remember yesterday you guys were talking about this being negative, was it yesterday? No, that was yesterday. This being negative, I switched it up, got a negative I, and I'm like, oh wait, switch it back. Okay, and then if you look at the diagram, it makes sense actually afterward. Silly rabbit. 50, what next? 3? 53? Guessing that's this one here. Yeah.
It's 54 that we've done maybe 5 times. Don't get it.
Oh, 54 is easy. Yeah?
I get it.
I'm kidding. It's not easy. It's definitely not easy. I shouldn't have said that. It's not easy at all. This is the judo guy, right?
Yeah.
Where you pull and kick at the same time.
Yeah.
You're just doubling the torque. Or not doubling, but you're increasing. The kick this way increases torque. The pull this way increases torque. So you're just that's how that karate move works. It just creates rotational inertia in one direction. Well, you've done that many times already, yeah?
Well, we've done this problem every single time period that we've been doing rotational inertia. We've done this karate problem.
Well, all right, it's not till the next one. Maybe we'll skip and come back, but we can go over it all. Maybe it'll help you, enlighten you a little bit about it. 53 is actually really quick. So if we look at 53, we've got a disc here. It rotates about its center like a merry-go-round. The disc has a given radius, a given mass. It's at rest to start. It starts at time 0. 2 forces are applied tangentially. That after 1.5 seconds, you have a certain angular velocity. So what can you calculate if you have a certain time period, a final velocity, an initial velocity?
Angular acceleration.
Again, angular acceleration. And you're going to need that for this one again. Okay, you're going to need that once more here. Let's see. So we could start with that first. We have omega final equals omega initial plus acceleration angular times time. Is that how you write it? Do you use omega I or omega 0? Zero. That's fine. Not. That is the appropriate term in college. You see, not. I use I in my class for initial because students confuse it with 0. But this is the right way to do it. So final equals initial plus AT. Is there anything squared or anything here? Am I missing?
No.
It's the direct analogous formula from the linear terms. So solving for A.
I think it's 2 alpha G. Yeah.
No.
The other one is squared and it's 2 alpha. And that's 2 alpha theta.
V over time. Not the third big degree.
It's like that one, right?
Yeah.
Yeah, the squared one and with the 2 comes in all together, yep. All right, so we'll use this formula to solve for A. I don't have these numbers written down. I did it all with variables. What would you get for alpha in this case? What would you get for alpha? What does it come out to be for, Dave? 250 over 1.25?
Yeah.
So 25 over 1.25 or... It's going to be 200, I'm guessing? And this is going to be radians per second squared. Is that correct? Now, if we have alpha, right? We have alpha. We've got forces acting on this body. We know that the total torque equals I times alpha. What's I in this equation? What's I in this equation? Where are we going to find it? A table, right? What part of the table are we looking at for this one? It's table 10.2 again. I've got the page, I think.
Yeah, I think there's one.
Yeah, I think choice C from the table says solid cylinder or disc about its central axis. So it's 1/2 mr squared is what we're going to use for this one. So we've got tau net equals I alpha. All right, tau net equals I alpha. Tau net, we have to consider there are two taus here. We've got F2. Go back to the diagram if you need to. F2 is going to make it go counterclockwise this way. F1 is going to make it go clockwise this way. So I've got F2 times, and they're both perpendicular, which is wonderful. Whenever tangent to a circle, it's always perpendicular, right? That always works out nicely. Times the radius r. Is the radius given in this case? I think it is, right? Okay, so we'll just put r for now. Minus F1 times the r value again. And that's going to equal I times alpha. I, we said, was 1/2 mr squared. And then that's times alpha, which is 200. I think everything else is given in this problem, right? What are we trying to find? F2. Okay. All right, so yeah, force 1 has a magnitude of 0.1 newtons. What is the magnitude of F2? Okay, so that's what we're solving for here. We're looking for F2. So just add F1R over and divide by R. All in variables, instead of the 200 there, you could have just put in omega final over time if you wanted to here. Okay, instead of 200, this is really final angular speed over time. That's how we solve for that, right? Yeah, that's what we saw. When we get this equation to solve for, we got that. So if you want it all in variables, this is what it's going to look like. And this little t, this t is in the denominator right there. Okay, that's what it would look like in variables. You take this expression times the angular acceleration, which is omega f over t, plus f1r, but adding it over, solving for f2, right? F2 is what I was looking for? So divide by r. Okay? All right. As a number, what do we get? Or if we can simplify this further. We can simplify this a bit further. Let's take a look at what it simplifies to. We've got 1/2 mr squared. The r's will cancel there, giving us 1/2 mr. And then that's going to be times omega f all over t. So I can get rid of the 1/2 and put a 2 in the denominator instead. And then plus f1. That's it, because the r's cancel.
Could you have factored out an r in the beginning?
Yeah, but once you factor r out of here and here, it cancels this r. You can factor. That's actually a good point. You could have reduced by r here, here, and here. Yep. Definitely, absolutely. All right, so you'll get an answer of 0.140. A value that I think is greater, right, than the other one was? Yeah, the other force was 0.1. This force was 0.140. Why do you think the second force was a greater value? Go back to your diagram, please. Why was the second force? Force 2 was pulling down this way on the disk. Force 1 was pulling down this way. Why was F2 greater than F1? Come on, make sense of your answer.
It's rotating now.
Which way? It's rotating this way. Remember your answer for angular acceleration was positive, which you guys have been considering counterclockwise. If you have a positive angular acceleration, it's rotating this way. The only way for it to rotate this way, is if the torque is more this way, right? Well, they're at the same distance from the fulcrum, so it's all about the forces, it turns out. Again, they're both a distance r from the rotating axis. So although we want to say that this torque needs to be greater than this torque, we could also simply say if this force is bigger than this force, it'll rotate this way because they have the same lever arm. So the torque and the force are interchangeable in the sense of which is greater causing the rotation because the lever arms are the same. This will always happen. Always. When you have what kind of a shape? A disc or a circle or something rotating with a fixed endpoint or some sort of a consistent radius. All right. Do we go to judo?
Yes.
Yeah? All right. 54. We got 2 more to go. 54 and 56. Like 2 minutes left? All right. So let's quickly go through 54 so you guys can see how this is done. Then maybe you can go over 56 with Mr. Donachek. Here we go. We got the judo guy here. So, a lot's going on here. You've already read this before?
Yeah, we done.
Okay, so to quickly summarize it, part A says, what if the force you apply pulling on the person's gi, right? So the gi?
Yeah.
When you pull on this, what if that force is negligible? What if there's really no force in part A? And then part B says, well, what if you pull with a certain force applied at a given height, h? So in the first answer, we're trying to figure out what the magnitude of the acceleration would be. Which is going to be greater, first of all? If I just kick your leg out and you fall, versus kicking your leg out and pulling on you, are you going to move faster the first time or the second time?
Second time.
Yeah, because you're pulling, right? So part A has to be less than part B. We should recognize that right away. If you kick somebody's leg out,
But then if you pull it back, it not go as hard.
you're kicking and pulling in opposite directions.
It's like
You're kicking the leg
spin.
out.
We're doing
Look, you're kicking them this way in the leg, and you pull them this way.
Okay.
So you're creating a rotation. I just lost airplay, didn't I?
Uh,
All right.